Do you ever stop and wonder what you'll think of that new fancy smartphone in your pocket 10 to 20 years from now? This is the Motorola Dynatac, one of the first commercially available cell phones. And by every account, this was an amazing marvel when it hit the market in 1984. It weighed about 2 pounds, took 10 hours to charge, and at a cost the equivalent of $10,000 today, offered only 30 minutes of talk time. Want to use one? That probably seems like a silly question, because obviously the technology today is obsolete. But it's also our lifestyles and our expectations that have become obsolete as well. Back in 1984, I could not imagine being or even wanting to be constantly reachable 24/7. Back before the internet and cell phones, my wired landline at home or at work was all I needed, and if I was not in one of those two places, I probably didn't want to be reached anyway. If I did, for a quarter I could use a payphone. Today my kids don't know what a wired phone or a payphone is. They can't imagine not being permanently tethered to the internet, and they think the primary use of that wall plate in their bedrooms is Ethernet. In 40 years, we've gone from this to this. Cellular communications has become integrated into virtually every part of our lives. Forgetting your phone isn't just an inconvenience, it's disorienting. There's actually a term for it, nomophobia, which describes the anxiety we feel when we're separated from our phones. In hindsight, this technology progression seems so obvious, but as we were working through these innovations, the path forward and the shift it represented just wasn't as clear. So how did we get from here, and what's coming next? When we made the jump from our kitchen phones with the tangled cords to our big Gordon Gecko phones, which we'll call 1G in this video, our focus was on making person-to-person voice communication anywhere possible. The primary value proposition of 1G phones was a new level of mobility. With 2G, the price, weight, size, and battery life of mobile phones got much, much better, to the point that they were desirable for regular consumers like you and me, and thus adoption increased. This is probably when most of us got our first phones. The value proposition of mobile person-to-person communications was the same in 1G and 2G, but 2G raised that value significantly, leading to broad, economy-expanding commercial success. 2G worked great for person-to-person telephony. But during that time, having the internet on our tethered PCs brought new forms of communication like email, and gave us access to unlimited sources of information on the web. And while 2G was just rolling out, engineers and scientists were already dreaming of bringing the power of the internet technology into the palms of our hands. And so the next two generations, 3G and 4G, were about connecting people to the internet. Few of us could conceive of the personal and business impact of connected apps, gaming, photography, streaming, video, and social media at the time. And now, once again, we can't imagine living without them. 3G was the big, bold step forward in making this vision a reality. But do you remember the early days of 3G, when neither your voice nor your data connection was guaranteed when you traveled, or even reliable when at home? Just as 2G improved on 1G, 4G improved on 3G, with faster data rates and better coverage across the globe. And now, we're just at the beginning of the 5G rollout. What's the new breakthrough that we just can't completely see that will be so obvious to our grandkids? First, it's really important to understand that a G, as in 3G, 4G, and 5G, is as much a consumer label or marketing term as anything else. Yes, these terms have at least a loose mapping to well-designed, highly engineered technical standards. But these standards are constantly changing and evolving and improving, even though we only label them a new G approximately every 8 to 10 years. The vision for these standards is set by the International Telecommunications Union, or ITU. As a part of the United Nations, the mission of the ITU is to harmonize spectrum use and communication standards across the globe. When the latest G is being imagined, much of the discussion centers around new target use cases. What do we need to be able to do in the future that we cannot do today? Standards bodies like the Third Generation Partnership Project, or 3GPP, bring together a lot of smart people in committees and subcommittees, where they argue, debate, and test their new ideas to see what works practically and what does not. And then they argue some more, debate some more, test some more, and eventually you get a standard where hopefully the best technology for the cellular ecosystem wins rather than the best politics. We need to have compatible, interoperable systems across all geopolitical boundaries to maximize the user experience and scale these technologies globally. And that really is only possible when everyone is working and testing against the same standard. Now we're in the process of rolling out 5G, which has been in the works since 2012. Just as the full technical and economic impacts of the iPhone weren't known when it was released, we still can't see the full picture of how 5G will impact us. But if history is any indicator, it's going to be significant. 5G is the first standard that I've followed personally from the very beginning seed ideas all the way through to what is now rolling out and being commercialized. As an engineer, that has been a ton of fun because in the early part, the dreaming phase, there are really no limits. It's all about promise and possibility and about positioning the very best technology to win. While 4G aimed at connecting people to the internet, the vision of 5G goes well beyond just connecting people to data, but connecting everyone to every device to each other. The wireless interconnection of every person and machine on the planet. There are 3 usage scenarios driving this 5G vision. The first is eMBB, or Enhanced Mobile Broadband. If we're going to connect everyone and everything, we need more data and streaming bandwidth. I think we can all relate to this, especially if you're streaming this talk or constantly on a video call at work like I am. The primary measure for eMBB is how many billions of bits of information we can stream every second. The second scenario is called MMTC, which stands for Massive Machine Type Communication. This is about connecting our billions of smart Internet of Things devices to a cellular network. For example, most of our IoT devices at home, like our smart thermostats or our automated lighting, connect over Wi-Fi or Bluetooth. But these are only useful to us as long as they're on our home network. So the goal of MMTC is to make any device work anywhere that a cell phone can go today. The primary metric for MMTC is density, or how many millions of low-cost, long battery life devices we can connect to our networks at any time. And finally, the third scenario is URLLC, which stands for Ultra-Reliable Low Latency Communication. If our Netflix stream goes down, even for a short amount of time, it is a huge inconvenience for sure. But if we want to run mission-critical infrastructure, like autonomous vehicles on our networks, then those networks must respond very quickly and be much more reliable than they are today. Now, even though we have the first 2 3GPP releases under the 5G name under our belt, we still have a long way to go before these capabilities will actually be available to most of us. As an example, in order to simultaneously meet the needs of more bandwidth, more devices, and improved response time and reliability in 5G, researchers and engineers began looking at using much higher frequencies than we've ever used for previous cellular standards. And while these new higher frequencies offer a lot of promise in significantly expanding 5G's capabilities, physics dictates that they're also a lot harder to use. While the frequencies used for 1G to 4G more easily traveled long distances and diffracted or bent around objects, the new millimeter wave frequencies that are a part of the 5G standard, with their smaller wavelengths, don't easily travel as far. And even though we've proven, both mathematically and through scoped field trials, that these higher frequencies can be used to deliver the vision of 5G, we still have a lot of work to do before every person globally has access to these new capabilities. Even here in the US, while I'm able to use 5G in the lower frequency bands, and while I have a phone capable of the new 5G millimeter wave bands, I have yet to be able to make a 5G connected phone call in the millimeter wave frequencies and to get the streaming performance that 5G is capable of. Engineers will continue to evolve and improve on 5G for several years at least. And while they are, the earliest researchers and thought leaders are already beginning to set their sights on 6G. There's a joke that the odd-numbered Gs are the revolutionary iterations, and the even Gs are the ones that get it right. We've already seen that with 1G and 2G, then 3G and 4G, and now 6G is targeting the same 3 use scenarios as 5G. Faster data rates, connecting more devices, and providing more reliability and security in order to connect everyone and everything. But for 6G to get it right, there's going to need to be some significant new innovations that can address the shortcomings of 5G. As an engineer for NI, I see 4 technology research areas happening under the 6G storyline that could do just that and help further accelerate 6G's value proposition. Number 1, going even higher in frequencies to get even more bandwidth and faster response. While 5G today uses frequencies as high as 39 gigahertz, 6G researchers are already talking about going to 300 gigahertz and beyond. Number 2, new multi-antenna architectures and technologies. By allowing our cell phones to connect to more than one base station at a time, we hope to improve the reliability and consistency of our connections. As we go to even higher frequencies, using denser antenna architectures can help overcome some of those distance challenges. Number 3, the adoption of artificial intelligence and machine learning. Huge advances in computing and software architectures made over the last decade offer promise in helping engineers deal with some of the hardest signal processing and software challenges of connecting everyone and everything reliably. And 4th, the combination of communications with radar and sensing. Truly intelligent devices need to be aware of the world around them. And by integrating radar-like sensing, we hope to unlock a new set of possibilities. Seem a little strange to be adding radar to your phone? Well, many of you already have a camera and a LiDAR on your phone. Radar is a similar concept, just at a different frequency. Now, as a fun exercise, let's try to imagine some capabilities that these technologies could enable, ones that we don't have today. Perhaps these are the things our grandchildren will take for granted in the same way our kids cannot imagine a world without an always-on data connection that also happens to make phone calls. So think about large-scale industrial agriculture, heavy machinery operating outdoors, working in huge fields and remote locations. Early autonomous vehicles for farming are already being deployed today. With high bandwidth, reliable data connections, the integration of multiple sensor types, including radar, and machine learning to ensure their safe operation while optimizing crop yield. And while most of us aren't large-scale farmers, remember the first applications are just the tip of the iceberg. Maybe you'll experience this technology as the end of lawn mowing as we know it. The babies being born today may very well roll their eyes at you when you tell them how you used to push a lawnmower around the yard in the heat for an hour every week. Will a machine cutting the grass all on its own be one of the many things that sound so futuristic to us today, but our grandkids will take for granted? Building on the prior example, let's consider the technology of a self-driving car. Autonomous vehicles rely on cameras, LiDAR, and radar to understand and perceive the natural world with roads, infrastructure, pedestrians, and of course, other drivers. These cars also count on acoustic and ultrasonic sensors to detect nearby objects and libraries of maps that are constantly updated and downloading from the internet. All of that real-world data is then brought together into an intelligent system so the car can make the right decisions. And the right decisions in this case literally save lives. With joint communication and sensing, the vehicle will process the reflection of its own communication signal to better detect objects ahead. And obviously, any cellular network used to help drive a car like this would need to be extremely reliable and very fast. Next generation coordinated antennas distributed along your route will track your car as you move, and machine learning algorithms will help the vehicle respond to complex, constantly changing road, weather, and traffic conditions to help you arrive at your destination more safely, more quickly, more comfortably, and more cheaply than the human-optimized mess we call rush hour. And last, let's talk about our health. In my circle of friends, we are all much more conscious of the foods we eat than we were just a decade ago. From pesticides to processed chemicals, we want to know where our food comes from. And for those dealing with food allergies to nuts or gluten, our health depends on knowing what's in our meals. As we pursue higher and higher frequencies for wireless communications, trending into the terahertz bands, we begin to reach frequencies which will cause different molecules to resonate in different ways. And by using machine learning algorithms to examine the reflections and absorptions off objects near us, we could, in theory, teach our phones to recognize the molecules in the food we eat. Imagine that. What if 6G candidate technology could enable our phones to finally tell us what the heck is in a fast food chicken nugget? Is it crazy to think of artificially intelligent cellular networks that can use sensing data to understand their environment and coordinate fleets of self-driving cars? Or to be able to wave our phones over a plate to tell us what's in our food? Things that are hard to visualize now will be the things our grandchildren take for granted. When you get a chance, thank an engineer. And always keep in mind, another G is coming.